So thank you for attending. What I would like to do is to tell you what we know, and more importantly, what we don't know about this earthquake. As far as scientists are concerned, seismologists like me, this is an earthquake that is like a book, and we are only halfway through the book. I don't know how the book is going to end, and we are on page 15 perhaps, and at the end of this talk we might have reached page 15 and a half. So there's a lot more to learn than anybody knows. And if you hear anybody predicting an earthquake, you must not believe them. It is not possible to predict earthquakes. And that's going to be one of the themes I want to tell you about. Okay, so having said that, I was asked to give a talk 3 days before this earthquake in Pasadena at the Seismological Society of America meeting. And they asked me to say where I thought the next few unexpected earthquakes would occur. And this was one of the pictures I showed. It's the Himalaya, and you can see there's a question mark right next to Kathmandu. I was more specific about what might happen here in Kashmir and in Bhutan, where we've done quite a lot of work recently looking at a combination of historical earthquakes and the current rate at which the mountains are being squeezed. And there's a question mark here. The question mark was there in my talk because we have a lot of puzzling information here that we are beginning to understand because of this earthquake. But this was 3 days before the earthquake. It's a big question mark, and it still is somewhat of a question mark. So let me tell you, first of all, something that you will probably, most of you know, and that is India is moving underneath Tibet. That is its destiny, to go under Tibet. And it's going at a rather slow rate, 4 centimeters a year in the west, 6 in the east, which means it's rotating counterclockwise slightly. And along this boundary, about half of this convergence is absorbed by the Himalaya. In other words, 2 centimeters a year is being absorbed by the Himalaya, and I'll explain exactly how we know that in a minute. The other 2 centimeters is going into squeezing the Tibetan Plateau and other mountains to the north. One point I'd just like to make is that if we wait long enough, the entire Indian subcontinent will have disappeared under Tibet. We have to wait a long time, but at that moment in time, there will be a long beach along here, the shoreline of Nepal with the Indian Ocean. Anybody who wants to invest in shoreline property, it will pay off in approximately 250 million years. Okay, how do we know these numbers? And this talk is all about numbers because scientists, when they have numbers, they're able to make forecasts about what the numbers mean. And we're able to understand the Earth and try to add to our knowledge, which can help us forecast future earthquakes. We can't predict them. We know we won't be able to do that. So what you're looking at here is a whole bunch of little arrows. These are GPS instruments. They are very precise. They can measure to an accuracy of 1 millimeter. Many of them are bolted to the ground with either concrete bolts or with steel bolts pushed into soil. But they are very stable, and with one or two exceptions. You can see a big arrow here. That's obviously a mistake. There might be a point on a hillside that's creeping downhill. We can reject that because it's an outlier. But from these measurements, we can construct what we think is happening along the Himalaya. So this is the same area. Now I'm showing the convergence rate between a blue line here, which you'll find interesting, and the frontal edge of the mountains, which we call the main frontal thrust, MFT for short. It's a crack, and the crack is where India is last seen before it starts going underneath Tibet. So this blue line is important, and so is this frontal thrust. Now, in big earthquakes, that frontal thrust moves. In this earthquake, it didn't. This is a surprise to us. And it tells us that we have to be careful how we interpret historical earthquakes. But look at the numbers a moment. In Kashmir, 12 millimeters a year, half an inch a year. Here, 18 millimeters a year, up 3/4 of an inch a year. Doesn't sound very much, but if you wait 100 years, 18 millimeters a year becomes 1.8 meters, about this amount. And if you wait 1,000 years, you get 18 meters, which is about the width of this tent. I put it like that because the earthquakes that occur here are usually 100 to 1,000 years apart, and they release some of that accumulated displacement. And that's shown in the next figure. These are the earthquakes that we know about, and of course there are many more, but I'm just showing the big ones. I'll show you what we think is the largest one we know about. It's a huge earthquake that ruptured hundreds of kilometers along the Himalaya. It started near Kangra and it finished near Takala. Unfortunately, we don't know exactly where it ended. How do we know anything about it? Well, we know at about dawn, at 6 a.m., on the 1st of June, 1505, monasteries were destroyed in 4 separate locations, and in the Takla Graben here, and the town of Agra was shaken so violently that most of the buildings collapsed, the tall buildings. The accounts, of course, from 500 years ago are very, very slender. They're not in any great detail. So we've had to make a lot of guesses about this. However, this earthquake did break the main frontal thrust. It made it slip, we believe, as much as 23 meters, the width of this tent. Huge amount. This is an earthquake that cannot occur more frequently than once every 1,200 years or so. And since it happened 500 years ago, it should not happen for 650 years. So there's the good news. This is a gigantic earthquake that happened and can't repeat because it hasn't accumulated enough energy. I can actually give you other interpretations about that, but let's leave that for the minute. Let's go to Nepal. The big earthquake that happened here in your recent history occurred in 1934. And that earthquake had a surface rupture. It made the ground heave in the Terai, and a number of distinguished scientists have excavated that mound of dirt, and they found cracks caused by the earthquake in 1934. They have also found cracks from another earthquake that happened there around in the 13th century. And since there was a very large earthquake in 1255 here in Kathmandu, they believe that that earthquake was the 1255 earthquake. So here we have a very important example of an earthquake that ruptured in eastern Nepal and came towards Kathmandu. As far as we can tell, it didn't get past Kathmandu, it stopped over there somewhere to the east. And this earthquake is a repeat of a previous earthquake. Now this is very important because it tells us that earthquake in 1934 shouldn't occur for another 600 years or so. Again, this is kind of good news. But I'm going to tell you about another earthquake that happened here in 1833. Okay, so 1934, 1833, they sound a bit the same, but they're 100 years apart, of course. The 1833 earthquake is very, very important for this talk because we believe that the present earthquake is a repeat of that one. And there are good reasons to suppose that. The damage was sort of the same, the area of the rupture was approximately the same, and we know quite a number of things about it. And I will tell you what happened. There were 3 earthquakes on one day. The first one occurred at 5 o'clock in the afternoon, and everybody ran outside. Now, you've all experienced earthquakes quite recently, so you know that would have had to be quite a violent earthquake to get everybody to run outside. Okay, let's say it may have been a magnitude 6.5. I say I'm low, guessing it was low, because the next earthquake occurred 5 hours later at 10 in the evening. And people had started going inside at 10 in the evening because it was dark, and they thought, no more earthquakes, but it's safe to go inside. And then the second earthquake was more violent than the first one, and they all came running out and started talking to each other and thinking, well, my goodness, we're going to have to get some tents out and things. It's now dark. It looks like we might have another one. And almost before they'd finished that sentence, a half hour after that second earthquake, the big earthquake happened. And that would be the same size as we've had right now, 7.8. Now this was the almost perfect sequence of earthquakes to save people's lives. It brought people outside, and they'd already been considering tents and things. So the loss of life in that earthquake was very small, even though the percentage of buildings destroyed in the valley exceeded that in the present earthquake. And that's because the buildings were weaker then, universally weaker. There wasn't any concrete. So that fabulous sequence, I'm afraid, did not occur. Instead, you've got the big earthquake first and the aftershocks later. And that is the precociousness of the Earth. It doesn't always do what it should do. So, let's move on. Now, scientists like me have been measuring with GPS, and we thought maybe we should try to indicate where the most dangerous places in the Himalaya are in terms of what we call slip deficit. So remember, India is moving northwards and squeezing the Himalaya, and we know that there haven't been any earthquakes in part of the Himalaya for many, many years. And so we're able to say that these sort of thermometers, if you like, tell you how much slip is ready to go if an earthquake happens right now. So the information is simply, we know there wasn't an earthquake here for 500 years, so we now know there's 10 meters of slip ready to go if an earthquake happens today. This doesn't say we're predicting anything or forecasting anything, we're just saying we know how much energy is now stored here, here, and here, and here, and here, and here. Notice there's more than 10 meters in 3/4 of the Himalaya, so there are a lot of very large earthquakes overdue. We just don't know when they're going to occur. The black dots indicate the population centers in the Ganges, and one of the problems with these big earthquakes when they occur, of course, they shake the Ganges plain, and a lot of damage occurs to the south of the Himalaya. Patna was damaged in this earthquake, even though it's hundreds of kilometers from the epicenter. So this is not a very helpful thing. It just tells you how much energy is there right now. So we tried now to put in a little bit more information about historical earthquakes, and we came up with a figure like this. Now, we made this in 2005, and it's not completely wrong, but I want to emphasize that what scientists do are use the best available information, and we offer that as this is what we know. We're just people that say this is what we know. And if we are delighted to admit we're wrong and to revise our estimates. Now what you can see here is that in the region of the 1934 earthquake, we said you could have a magnitude 7.9 if it happened right now. Well, here in Kathmandu, the estimate was a 7.4 earthquake, based on the repeat of the 1833 earthquake. We were quite wrong. What actually happened was a 7.8, somewhere between those two estimates, in a slightly different place. So this is not an accurate view. This is the best shot we had in 2005. Now we can revise it. So this is this is the best shot today. We know we have many earthquakes overdue in Kashmir and in Bhutan and Arunachal. We don't have to talk about those now. What we have is a sequence of earthquakes in the Kathmandu region, 1255, another in 1344, one in 1833, and this earthquake. And this, we're going to build up a story. I'm going to tell you numerically what we've learned about it. But first of all, something scientific, something interesting, something elegant. This blue line, which I mentioned before, everything above 3,500 meters is colored white in this figure. Everything below 200 meters is colored green. The Himalaya is where all the earthquakes occur, and they occur between those two different color bands. That is kind of interesting. But what is more interesting is this. If you put a pin in a point near in southern Mongolia and had a piece of string stretched to this point, you can draw a perfect circle on the Earth's surface. Of course, this is a map, so it doesn't quite look like a circle, but that circle follows this interface between the brown and the white all the way along to within about 5 kilometers. This is remarkable if you think about it. This is the Earth showing an elegant simplicity that tells us there is something really important underlying the shape of the Tibetan Plateau and the northern edge of the Himalaya. Now, the blue line is also a very important line for another reason. Between big earthquakes, like before 3 weeks ago, thousands of micro-earthquakes occurred along this blue line. It followed that wiggly line, the 3.5 kilometer contour. Okay, and it signifies there is something menacing going on underneath the blue line. And in fact, 18 kilometers below the blue line, we know the Indian plate suddenly gets very weakly coupled to the base of the Tibetan Plateau, and it slides underneath. I'll show you a contour of that. Let's have a look. Now, first of all, how do we know so much about this blue line? It comes from this. I'm going to have to tell you something a little bit about data. Each little cross here is a GPS measurement made in Nepal, made in the last 25 years, and there is a red line that you can see approximates those data. And what this is the convergence of the Himalaya. This is 0 millimeters a year, this is 18 millimeters a year over here, and you can see there is this perfect curve, and we know that perfect curve can be caused by only one thing, and that is a locking of the Indian plate southwards and the movement of the Indian plate northwards. In other words, this is where there's a huge buildup of stress. And you can see that in the vertical, the stress causes the mountains to rise about 5 millimeters a year. So Everest has been growing 5 millimeters a year, and there was an earthquake in 1934. It was climbed in 1950. In other words, it had just collapsed after the earthquake, and it's now growing. In other words, anyone who climbs Everest is now climbing a slightly higher mountain than was climbed by Hillary. It's an interesting thought. But this uplift is a measure of the spring being squeezed. If you squeeze something, you make it taller in the other direction. Think of a piece of rubber. You've all tried this. You know, you can squeeze the rubber, its dimension goes upwards. That is elastic strain, and that's what's happening in the mountains here. So these are the data that give us a model of what's going on. Here's that line, here's the uplift, and you'll notice this red bullseye. That is where all the stress is being developed. In a region around here, the rocks are all being squeezed. North of that line, the Himalaya, the Indian plate, which is this thing here, is able to move slowly underneath without any resistance underneath Tibet. South of that line, the Indian plate is glued to the Himalaya. It's a kind of difficult concept, so I've got a little model to show you. It looks like this. Here is the region where stress is built up. The top is being squeezed, the mountains are rising. The bottom is under tension, the Indian plate. And the Indian plate here is moving all the time, but here it's locked. So as I go through time, 30 years later it looks like this: 60, 90, 120, 150, 180, and then I get to a point where the stress here is so big, it exceeds the strength of the rocks underneath the Himalaya, underneath you, underneath this tent. 10 kilometers down, there is something about to happen, and that happens like this. Ah! I knew I would press the wrong button. Okay, Back. All right, so the great earthquake happened. Let me just switch between these two a moment, and you can see some things happening. Here, there's a compressional stress. After the earthquake, it goes down because the stress is released. Here, the stress is increased and the rocks go up, okay? And this whole package of rock here, which is in fact the Himalaya, it's 18 kilometers thick at the back and about 2 kilometers thick at the front. It all slides forward. Now that has been the model we've been using for all earthquakes. It's certainly what happened in 1505 and it happened in 1934. A rupture appeared. All the energy from here was driven to the front and was dissipated as soil in the fields of the terrain. Now what actually happened in this earthquake was very different. But let me show you how violent this process is. Okay, nobody living here, okay, it's just forest, so nothing to be feared. But what you can see is a man here, and you can see a dark layer of soil. The soil continues over here. And there is a layer of soil that runs through here and peters out about here. This distance is 23 meters. And what you are probably puzzled about is what you're actually looking at. What you're looking at is a wedge of rock that used to be over here somewhere in contact with the soil layer, and it got pushed up in the air, and then poof, it landed. And all the trees on it, in 1505, were obviously tilted in the direction of the movement. This is the main frontal thrust, the MFT, that slipped in 1505. And you can go all the way along the Himalaya and find giant earthquakes that have left the same kind of message. And this guy here, Steve Wisnowski, is removing little particles of carbon-14 to find out when it slipped. And his particles tell us it slipped probably in 1505, maybe perhaps a little earlier. So, unfortunately, what happened in this earthquake was nothing like that. What happened was that the strain energy in the Himalaya, in the high mountains, was delivered not to the front, but to a point just south of you, here in Kathmandu. This is really very puzzling for us, but we know this is what the Earth does, so we're learning from it. What it means is that something has to happen to the south of this great pile of rock and stress that's been delivered. I'll say it again, the stress that was there has been 2/3 dissipated in moving the valley, and then 1/3 of the stress remains to the south of the valley. I don't think you have anything to worry about this, because I'm going to explain there are 3 possible explanations, and I hope that the least inconvenient one will occur. This is what we are talking about. During the period between earthquakes, the Indian plate is sliding over here. Normally, when an earthquake happens, a rupture appears and delivers all the stress to the terrain. But in this earthquake, what happened is it was an incomplete rupture. It stopped just south of you. Okay? And it's probably a good thing. We think that may have had something to do with the low accelerations in the Kathmandu Valley, which I will be talking about. Now, all the seismometers in Nepal were shaken so violently by the earthquake that they weren't able to give a very good indication of exactly what happened in the earthquake. But seismometers throughout the world recorded this. This was recorded in Australia and New Zealand and South Africa and Antarctica and America. And by taking all the seismic waves and analyzing exactly what they did, we came up with this. This is what we think happened. There are various refinements on this, but this was an early one. And what you can see is the epicenter here, Kathmandu there, a kind of blue region, that's what slipped, and this red region, which where things slipped about 4 meters. So 1 meter, 3 meters, 4 meters. Those are what the colors tell us. Now, I'm going to emphasize, this is the slip on something underneath you. This is 10 kilometers deep here, it's about 20 kilometers deep there. So this is like an X-ray view of what happened in the earthquake. It's absolutely amazing. These little dots are the micro-earthquakes between big earthquakes. They tell us about where the stress is that happens that gets released in an earthquake. And you'll notice that maximum slip occurred where there's a lot of these little dots, micro-earthquakes. So, yes, we were right. Most of the energy was stored here, most of the slip in the earthquake occurred there. But what actually happened is nothing short of amazing. I'm going to tell you something which I want you to try and grasp. We call it a thought experiment. Let's think of a brick, okay? A brick is about 4 inches high and about 10 inches long, okay? It's a red thing, and if you drop it on your toe, it hurts. Now, imagine now a big brick, not 4 inches high, but 4 miles high, and 10 miles long. One of the interesting things about a brick, if you put it on a piece of concrete, is you can slide it very easily. Now, can you slide a brick 4 miles high and 10 miles long across concrete? The answer is, believe it or not, yes, you can just do it. If you have enough force, you can push this mountain of brick across the concrete. But now, if you put another brick in front of that brick, the same dimensions, so it's now 4 miles high and 20 miles long, you cannot push the brick. And the reason is that the force pushing against this brick breaks the back surface of the brick, because the brick is not strong enough to overcome the friction. Instead, the brick simply breaks. Now, what I just told you is an analogy for the Himalaya. What I'm saying is the Himalaya is 18 kilometers high. It's about 100 kilometers north-south. And if I push it with Tibet, I can't make it move. It cannot move. Now, obviously, this is an absurd paradox because it did move. So something funny has to happen, and we know of two mechanisms that can do it. The first is that as the rocks begin to move, they get hot and melt, and suddenly the friction goes to zero and the thing can slip. We know that some earthquakes actually do that. But we have another explanation which is even more remarkable, I believe, and again it's something that can relate to you. Imagine you have a large carpet and you have to move it. What you would intuitively do, because you know about carpets, is you pull it. You would not push it. It would be absurd to push a carpet. Why? Because as you push the carpet, it wrinkles, okay? It actually becomes deformed. That's exactly what the brick is doing. You cannot push it because there's too much friction. If the carpet were on ball bearings or sitting on skateboards, you could push it. But it's sitting on something where there's too much friction. Now, some of you will have actually encountered this problem and know that you can move the carpet by pushing it if you do something. You have to give it a flick. I just put the microphone down and pretend to do it. You go like this. That jerk sends a ripple along the carpet, and the far end of the carpet will move an inch. It will increment forward because of this ripple. So let's imagine a ripple. What is a ripple? It's a point where the carpet goes up in the air and comes down again. It's connected at the front and the back, but there's a ripple here, and that ripple propagates forwards, just like the ripple on a pond. But as it propagates, there is a space, there's a gap, and that gap implies zero friction. So we believe that some of these gigantic earthquakes, like the Tohoku earthquake and the Indonesian earthquake, actually slip like that. And that is what we think happened in this earthquake. A ripple went underneath Kathmandu and translated it. Let's see how fast it moved. 5 seconds, 10 seconds, 15, 20, 25, 35 seconds after it leaves the epicenter, it arrives here. You can calculate the velocity, 2.5 kilometers per second. Doesn't mean anything. It corresponds to 5,600 miles an hour. It really rippled towards you real fast. It just whizzed towards you, and then when it got to the outskirts of Kathmandu, it slowed down. I mean, this is a fascinating discovery. What is the amazing thing is that the ripple, the increment of the carpet forward, the carpet mode, it caused Kathmandu to move 1.8 meters in about 5 seconds. So everything before the earthquake was on this side of the table. After the earthquake, it had moved the width of a table. not aware of that. This is a gigantic slip, and to my knowledge, no capital city has ever in recent history been moved like that in an earthquake. Now, why is that so unusual, do you think? Because most of the collision zones where this kind of subduction of a continent going underneath another continent, a plate tectonic collision, is under an ocean, Tohoku, and the Indonesian earthquakes. These are all ocean-continent collisions that result in disturbing the sea floor. There are no capital cities on sea floors. This is a very, very unfortunate location for Kathmandu. Now, having said that, the accelerations in this earthquake were very much subdued. I'll show you. This is another view of that process. Another source of data from this earthquake comes from outer space. It comes from satellites that are looking down on the Earth and illuminating the Earth's surface with radar every few weeks. And this is a comparison of the Earth's surface before the earthquake with the Earth's surface after the earthquake. And you will see rings here. Here's Kathmandu. Here, this is the Terai. The high mountains are over here. This region sank. This region rose. This is the bulge that is centered near Kathmandu. And you can see nothing happened here, which tells us that the rupture didn't make it to the Terai. And this is a very accurate view, and this image is being updated about once a week, so we can see from space exactly what happened. And this is a summary view of what we know so far. The 1934 rupture, the 1505 rupture, assuming it came to here. This earthquake, outlined by the aftershocks that you are now feeling, the aftershocks are beginning to grow outwards because of the stress caused by the incomplete slip. And there is a region here that has not slipped. Now, why we're worried about that is because the Indian plate, you know, the destiny of the Indian plate is to go underneath Tibet. It has to slip. If it doesn't slip, it will cause a mountain range here. Well, hello, there is a mountain range, the Mahabharat range. Could this be the mechanism that keeps the Mahabharat up? Possibly, but we think the Mahabharat was raised about 2 million years ago, and it should be inactive now. So we think there is a region here that will slip in the future, and how it slips is kind of important. Is it possible that we missed some slip here? Well, yes. The image here, this is the same image you've just seen, had a little dislocation here, and we thought, maybe the fault slipped. Maybe this is good news. Maybe it's actually slipped and will slip a little bit more. So we looked at these cracks and went down to the Terai to look. It's about 30 kilometers to the east of Hatauda. And here are some farmers in a field, and here's a crack. We landed next to the farmers and said, have you seen any cracks? And they said, yes, yes, come and see our crack. They knew so much about their field. It was absolutely amazing. They took us to a couple of hairline cracks, and this was the largest, and it's about 2 inches wide. During the earthquake, water gushed out of it, a well nearby, emptied, it gushed up water, and after the earthquake was over, they found the well had been completely blocked by sand. Now this is a process we call liquefaction. Not much liquefaction happened in the valley here, but there was a lot in the Terai. And so we were able to, first of all, see this crack from space. Think about that a moment. Okay, it's only 2 inches wide, but we could see its effects from space. We went there, checked it out, and were able to confirm that this was not the main frontal thrust that had moved. So as far as we're concerned, that one is still to go. Okay, this is a plot of aftershocks. It's plotted in a different way from the way you normally look at these aftershocks, because this is 1 day after the main shock. This is 1/10 of a day, 2.4 hours. This is 1/100th of a day, which is 2/3 of a minute, okay, 40 seconds. And here we're looking at about 4 seconds after the main shock. And what you can see is the main shock happened in the west, blue color, the next aftershock was right here in Kathmandu, 100 kilometers away, and still within a fraction of a minute, an earthquake happened in the far east. And this sort of progression tells you how the earthquake communicated that it had happened to distant points of Nepal. It's the seismic wave propagating across and stressing regions that are just about to go. Now, the other interesting thing about this plot, it shows the large aftershocks that alarmed you. This is the 7.3 with its own suite of aftershocks that occurred. And it's all condensed on this plot because of the logarithmic scale we're using. But what's interesting, these are more or less uniformly spaced in time. And that tells you what we know always happens in an earthquake. The aftershocks occur exponentially decreasing in time. In other words, they are further spaced apart, and their amplitudes keep getting smaller and smaller and smaller. So they will eventually disappear. So this is kind of good news, except for these anomalous ones. And in the 1833 earthquake, for example, there was quite a violent earthquake. It must have been comparable to one of these 6.5 or so that happened in 1835, 2 years after the earthquake. There was also a very large one in 1866, which I'll talk about in a second. So what actually happened in the valley? Well, this is a seismogram measured by an accelerometer, and it tells us numerically how much shaking occurred. You can't see the scales, but they're all the same. These peaks are shaking to the east and west with amplitudes of 0.2 G. What does that mean, 0.2 G? Okay, if I jump in the air, I accelerate by about 1 G. That's what I do. In order to leave the Earth's surface, you have to accelerate by 1 G. And if you have a building accelerated into the air, it's not good for it, I know, but it has happened in some earthquakes. Not this one. This earthquake was very benign compared to the sort of accelerations that some people expected. So these accelerations are low. The other thing you can see is the frequency. You can't actually tell, but these are 10-second intervals, and you can see you get 2 wobbles in 10 seconds, so the wobbles have a period of 5 seconds. They go something like this, which was the period that gave you all great deal of trouble standing up. I've seen people, movies that look like this, and that's caused by the ground moving backwards and forwards at this very low rate. Now, if you take this signal and you integrate it twice, calculus for ICIMOD. No, it's okay. What you can do is derive the displacements that occurred in this earthquake, and they look like this. This is from the seismogram. It looks as though the ground moved about 1.5 meters. And normally in an earthquake, that's all the information you have. From the accelerometer, you derive the displacement. In this earthquake, something marvelous was available. GPS receivers recording not at one sample every 15 seconds, which is what we normally do to study earthquake movements and plate movements. These GPS receivers near you, one on the northern side of the valley, these top 3 traces, and one at Nast, in the middle of the valley, they were operating at 5 samples per second. Okay, 5 samples per second sounds a bit like this. Really fast rate. And it was possible that you can actually see the little dots on this. We know that the valley moved at 50 centimeters a second for a brief period of those 5 seconds when displacements occurred. So I'll just rattle off what happened. The northern part of the valley moved 50 centimeters west, 1.8 meters south, and 1.3 meters up. Okay, these are really big numbers, by the way. In the middle part of the valley, the same westward displacement occurred, slightly less southward displacement, and slightly more vertical displacement. Sorry, less. It's 1.3, it's about half. Now, Look at these two traces. I'll tell you what's happening. This is the displacement in 5 seconds of the vertical. And then once it gets there, it stops there. So everything in Kathmandu is now somewhere between 1 meter and 0.5 meter higher than it was. The northern part of the valley is a little higher than the southern part of the valley. So everything is tilted. A little bit, okay, less than a degree. Don't worry about your sewer, it probably won't get blocked by this. But of course, the direction of water depends on the direction of the vertical. So there's been a little bit of tilt, and there's something amazing happened. You'll notice that the east and the north signals in the rock part of the displacement curve are quite static. They overshoot a bit, but they get fixed quite quickly within 10 seconds, where they're going to be for the next 100 years or so. However, in the valley, look what happens. The lurch of the valley caused the sediments to oscillate at about a 5-second period. In other words, it's the sediments that cause this wobble. The sediments you can think of as a bit like a large bowl of curd, very large bowl of curd, 20 kilometers across, and as you shake it, they continue to wobble. That's what happened in the valley. And what is perhaps very fortunate is that frequency is low. If it were 1 second or half a second, there would have been an enormous amount of damage to the buildings. But because it's 5 seconds, not much damage was done. Again, we have to thank the Earth for dealing us an earthquake that was not as violent as it could have been. It was, of course, dangerous, but it was, things could have been a lot worse. So these records are absolutely remarkable, that nowhere else in the world have we seen such a perfect description of what happened to a city. Where do they come from? Well, mathematically, you can show that a layer of sediment or curd will oscillate backwards and forwards with a frequency of, or a period of 10 seconds, if it's 650 meters deep. Okay, that's a mathematical result that comes out of a textbook. The Kathmandu Valley is only a maximum of 650 meters deep. You can think of it averaging perhaps 300 meters, and that means you get a resonance of about 5 seconds. It's the sediments swaying backwards and forwards until they're damped by internal friction. Another thing that happened in the valley that's quite surprising, there are ridges throughout the valley, and the damage is preferentially focused on those ridges. If you imagine a ridge sticking up like this, being shaken laterally, then you can also quite easily see how you might get amplification. So that accounts for a lot of the damage that's very, very localized on ridges. Okay, summary so far of the science. What happened is Tibet is like a brick wall, you can't do anything about it. The Indian plate is this triangle and this black line, and as I push it, I can push India underneath Tibet. But as I do so, I squeeze this spring, and Kathmandu I'm going to put on roller bearings because of this strange carpet pulse. And when the earthquake occurs, this spring suddenly lurches forward, pushes the valley as though it's on skateboard, and it squeezes this region here, the squeezing motion that I described before. And the big question is what will happen just to the south of this region that's been squeezed, because this also is acting like a spring. Now, the lurching in the valley caused some cracks, and if you take imagine a cross-section across that crack, this is the one that some of you will have seen on the road going east from the airport. You can see I've depicted this as a kind of a chunk of land that's slipped downwards. We call it a graben. Any houses across the crack, here's the crack, were tilted. One of the amazing things about this crack is it didn't occur in the earthquake. It happened after the earthquake. It happened at the end of this sloshing motion. And we know that because the little old lady came out into this courtyard after the main shock looking for her husband, couldn't find him in the courtyard, and the courtyard was just perfect at the time. So then she saw him. and ran and got him from where he was, sitting on a bench in the road, dragged him into the courtyard, and suddenly this crack appeared. She was able to describe that it happened about 30 seconds after the main shock. And this is something that's quite common. We know it's not a surprise to us. Liquefaction phenomena and sediment slumping is something that follows earthquakes. So I'm now going to just show you what we think might be happening in this region. This is what we know happened. This is a cross-section. It shows the rupture producing Uplift, the bulge just south of the city, or near the city. And we're able to make a map like this. Here's the rupture zone. Okay, north is now slightly off in this direction, so this is parallel to the main frontal thrust that we know is able to release this energy and must do so to allow India to move southward or northward. So this region hasn't slipped, this region has slipped, so we're able to develop some scenarios. Now, scientists develop scenarios because we need to develop tests to see what's actually happening, so we have to have a good idea of what we think is happening, and then we do some measurements to see whether in fact that is what's going on. And this is what we think is going on. Right now, we had our earthquake rupture. This region is stressed. Here is Kathmandu. It's gone up a bit. The mountains have gone down a bit. What's happening here? Well, here are three possibilities. The first, and the most likely, is that creep is occurring. Creep is a process where you can slide your brick over the concrete simply by putting grease on the concrete. It just is slippery enough to slide. In other words, you can't have an earthquake because as soon as you push, the brick moves. So this is very probably what's going on. And in conjunction with scientists in Tribhuvan University and NAST, we're helping them put measurements across this zone to see whether that is indeed what's occurring. If that's what's happening, fabulous. But then there is another possibility. This is scenario number 2, and that is this might go in an earthquake. We have to admit it could go in an earthquake. I'll explain why in a minute. But if it did, it has enough area to be a 7.2 or greater earthquake. So we hope that's not what's going to happen, and if our measurements are in place quickly, we will be able to see whether or not the displacements have stopped here or whether they're moving forward. So we'll be able to distinguish these two hypotheses, hopefully in a week or two. The third possibility is something completely different. That is, the Indian plate, which we're always forgetting about, is a participant in what's going on. The Indian plate has suddenly been released. It's allowed to start sliding deeper under Tibet. And in fact, in the earthquake, it suddenly was allowed to slip 3 meters or so, which means it's put this region into tension. And this region is very sensitive because it bent. As India goes underneath Tibet, it flexed downwards. In fact, it's about 6 kilometers down already here. South of Bihar, it approaches the surface, but here it's 6 kilometers deep, here it's 18 kilometers deep, so you can see the bending. And if you bend something, you will put the top part into tension and the bottom part into compression. And some of you may realize I'm describing something very similar to what happened in 1988. The Udaipur earthquake was an earthquake down here, deep in the Indian plate, or somewhat beneath it, 40 kilometers down. It was a 6.8, I think, or 6.9 earthquake. That's something else that could occur. Our measurements may be able to tell you. So here is almost my last picture. This is a summary of what we know, and I think you'll find it interesting. The red dashed line is the current earthquake rupture zone. Roughly, it's very approximate. The green area is the region we think slipped in 1833. We know about that earthquake only from what people wrote down in their newspapers and described and how they felt, whether they could stand up or whether buildings were damaged. So we actually do know quite a bit about it, but this is somewhat conjectural. But to a scientist, that's an almost perfect match. Now we know it's not a perfect match because in the 1833 earthquake, the region near Gorka only had 2 houses damaged. In this one, it was almost total damage. So it's possible that the 1833 earthquake propagated from the Kudari region to the west, whereas this earthquake propagated the other way, which would explain perhaps the difference in damage. We don't know. It doesn't really matter. It's good enough for us to realize that we have a replica, a template of what might happen in the future here. So what happened after 1833? There were lots of aftershocks. People described aftershocks going on for months, and there is a specific account of an earthquake that happened in 1835, 2 years after 1833. Nobody knows where it was, but it would have been much smaller than the main shock, so we can almost guarantee it was not a 7.8, but a 6 point something, 6.5, 6.8, but it was enough to alarm the citizens. 2 years away. So it might happen any time from now to 2017, so you have to be on your toes, but it's not as bad as that main shock. And then we also know about an earthquake that happened in 1866, and this sort of wiggly line shows scientifically our uncertainty. We don't exactly know where it was, but you'll notice it's in roughly the area we've just been talking about. Could this be an earthquake in part of the zone that's not slipped? We don't know. You know, one of the, at this point I will point out that there are a lot of things we don't know. Scientists are very bad witnesses in courts of law because we say what we know, and we are very, very careful to say exactly what we know at a certain period of time. And if things change, if more data comes along, we are also very happy to write, we were wrong. We refute what we said before because we now know more information. So as a scientist, I stand here before you very humbly saying I might be wrong about everything. But I'm trying to give you everything we know so that you become an informed citizenship. Okay? Here's some absolutely boring news about Mount Everest. For some reason, journalists are more interested in this so silly mountain than the dreadful things that are happening in this earthquake. I find it appalling. But this is a region of uplift, this is a region of subsidence, and you'll notice the Everest region is very close to a region where nothing happened. My calculation says Everest sank 1 millimeter. So that is not news, and I don't think journalists should be talking about Everest at all. Ooh. This is my last picture for you to show you the level of uncertainty that most seismologists offer you for this earthquake. There's a lot of there's a lot of controversy. There's a lot of suggestions about what they know. You may hear news accounts of people saying there's going to be another big earthquake. Let me tell you what we know. Here's the 1934 earthquake, an 8.4. We know all about that, except we're not quite sure how far it reached towards Kathmandu. The 1505 earthquake, we know quite a bit about that earthquake, but we don't know how far it approached Kathmandu. If it reached Kathmandu in 1505, or reached the rupture zone of this earthquake, which is shown in yellow, okay, Kathmandu is here, and this is the zone of 1 meter slip. If it reached that zone in 1505, then we should not have another big earthquake for about 600 years to the west of you. Okay, that's one interpretation. Unfortunately, the data that we have for trenching sites in this region are not very dense at the moment. And you can be absolutely certain that there will be an enormous amount of investigation to try to find out more information about earthquakes that may have occurred just here. Now, we do know of an earthquake that happened in this region. This black line is the frontal thrust that's been dug up, just like that slide I showed. It slipped in 1255 in this region, and 1344, a little bit to the left, and over in part of that region. So it's possible to do some arithmetic. You say, The 1255 earthquake was followed by a 1344 earthquake 89 years later, and the 1934 earthquake might be followed by an earthquake 89 years later, which puts it into 2023, 8 years from now. Okay, that's a hypothesis. And the French scientists who looked at this and said, well, 2023 is equal to 2015, it's close enough. They are saying this earthquake in 1344 was a predecessor to the earthquake that's just happened. Can you see the fatal flaw in that? In 1344, there was a rupture that met the surface here in the terrain. This has not happened in this earthquake. So this can't be a repeat of that earthquake. It's something different. And I'm hedging my interpretation on the fact that the 1833 earthquake resembled this in so many ways that it's possible that there might be another earthquake in your future, but not until 2048, quite a long way away. These are all conjectural statements. Nothing is certain. And if anyone wants to ask me whether there will be another big earthquake, my opinion is no. We've released all the energy in this region. Microphone has something to say. Sorry about that. Okay. Sorry. I thought that the electronics was going to prevent me making my prediction. No, I am not making predictions, and I hope you do not listen to them. The important thing is that this is a convergence zone between two tectonic plates. Earthquakes really do occur, but they do not occur sequentially. The one piece of good news I can offer you is that this earthquake looks like 1833, and 1833 was not followed by another big earthquake. It was followed by aftershocks. In 1905, there was another similar earthquake that did not rupture the frontal thrust in Kangra. That was not followed by another big earthquake. It was followed by aftershocks. So we have only 2 examples for you, but that's better than nothing. And even just with 2 examples, I'm willing to think that you will not have another big earthquake. This is just a personal statement. But I have to admit that we do not know, and we could be wrong. So you really must rebuild your houses as though you will have another earthquake. And that, I think, is the take-home message. Thank you.